All right, I think we are on time. Hello. Welcome to this session at J4K. My name is Bruno Borges, and I'm a product manager here at Microsoft, and I work behind the scenes on the Microsoft build of OpenJDK and other performance tools. And for quite some time, we have been working on some research on Kubernetes and Java and containers. And this talk is about to give you some perhaps potentially new information that you were not aware, and also some tips and tricks on how to configure your Java workloads inside containers on Kubernetes. So first, let's just let's see a quick recap of the agenda. So we're going to talk about JVM default ergonomics. We're going to talk about JVM garbage collectors, and then we're going to talk about Java on Kubernetes and what are the things that you should be aware of. And finally, a conclusion that hopefully gives you some good next steps. So first and foremost, we Java developers have heard these things about the JVM and how the JVM is smart and has a lot of ergonomics that will try to adjust itself based on the system. And that is true for a variety of reasons and for quite some time. And the reason for this is because the JVM doesn't know what application will run until it actually starts and runs the application. And the JVM also doesn't know the hardware until it actually is running. So that's why there are a set of default ergonomics based on information coming from the system, and then the JVM will size certain characteristics of it, such as memory allocation and threads. But and the garbage collection configuration. But there are a set of information that may or may not be read by the JVM during start. So we ask people, Java developers, just like yourselves, on the internet. And we ask a few questions about their understanding of the default ergonomics of the JVM of OpenJDK. First question that we ask is, how many garbage collectors are available on an usual OpenJDK distribution of OpenJDK 11, let's say? And this is the result of where people voted the most. So 49% believe there are more than 4 garbage collectors available on vanilla distribution of OpenJDK. And they are right. It is true. More than 4 garbage collectors are available on OpenJDK. But this is the interesting part. I mean, more than half, 51%, think that there are no more than 4 garbage collectors. So clearly demonstrating a gap on the understanding, on the knowledge about the garbage collectors on the JVM. So another question we asked was, okay, so when the JVM starts, the JVM needs to look into information from the system and then make a selection of the best garbage collector for that. And we asked the question, okay, what is the information from the system that the JVM will look into to make that selection? Is it the number of CPUs, the number of processors? Is it memory available? Is it both? Or is it the size of the class map? And luckily, very few people were brave enough to select the last part, perhaps surprisingly. Only 2.3% believe that the size of the class path is what the JVM will use to make a selection of the garbage collector. And yes, it doesn't make sense exactly, because you may have a very small class path, but an application that can be extremely heavy in terms of data processing and so on. So size of class path really doesn't make any sense. But what about CPU and memory? Most of them believe that both informations will be used, but both set of information will be used by the JVM to select a garbage collector, and that is correct. The JVM will, in the GC ergonomic selection, it will look into the number of processors, and it will look into the amount of memory available in the system. And based on those informations, it will make a selection of the garbage collector. Okay, so people understand quite well CPU memory is important for ergonomics, but is it true that the JVM will consider a variety of garbage collectors, or it will make a selection like I'll choose this one or that one based on CPU and memory. Or I might, or will the JVM select this one or that one or a third one, again, depending on the amount of CPU and memory. The majority of people believe here, 35.8% believe that all of the available GCs may be up to consideration by the JVM during startup time. 25% believe only 2 garbage collectors are coded by default to be selected during this process. 18% believe it's between 3 garbage collectors, and 20% are very honest, they just have no idea. The right answer is only between 2 garbage collectors. That is true. Only 2 garbage collectors. Besides having more than 4, the JVM will choose between 2, which one will be used based on the amount of CPU and memory. So we asked the question later, okay, do you trust JVM ergonomics? And 43% said yes, always. 21% said yes, but until now. 17% said they never trusted ergonomics, and 17.8% said they had no idea about any of this. So I think more than half of developers here are on the same boat as we have been researching, that there is a lack of understanding of default ergonomics, and that there is an opportunity to make things better. So yes, 74% believe that we could have better JVM ergonomics to really cover a wider range of scenarios. So we asked further questions on another survey. About 150 people answered this one. And we asked, hey, are you deploying Java inside containers? And 150 people said yes, yes, we are. And out of those, 65% of all of the survey said that they use up to 4 CPUs only. And 65% said up to 4 gigabytes of RAM of memory for the container. And about half, they said that their microservices or their applications inside the containers are quite I/O intensive. And by I/O intensive, usually this means either file or network. Network is also I/O. Overall, across all of the respondents, 48% are using no more than 2 CPUs, no more than 3 CPUs, and no more than 2 gigabytes of RAM. So it's interesting to see that there is a trend here of small containers with very few CPUs. And we can see on the chart that among the 65% that only deploy up to 4 CPUs, the majority of them deploy only 2 CPUs. And then there is a third, a quarter of people here, a quarter of people deploying only 1 CPU, containers of 1 CPU. And there is some people deploying 3 CPUs or even 4 CPUs. But yeah, the majority is 2 CPUs or even 1 CPU. And memory-wise, the majority of people, again, deploying up to 4 gigabytes. And within those, the majority are deploying 1 gigabyte of RAM or 2 gigabytes of RAM. We then asked a partner, an APM vendor, who monitors millions of JVMs in production, and we asked them, hey, can you share some data that we can understand better the deployments of Java inside containers? And they gave us this nice dashboard that shows 62, almost 63% of all the JVMs they monitor, millions of JVMs, 63% are inside containers. And of those inside containers that they monitor, the majority of them are actually using only 1 CPU and are using Java 8 at that time. This was about 2 years ago. This dashboard is from data from 2 years ago. I'm very confident that this trend has now changed a little bit, where Java 8 and Java 11 are closer. but it still shows a lot of usage of Java 8, but also growing usage of Java 11. But other interesting data points that we can see here is that the GC algorithm of many of the applications are G1 GC. Even though developers are using one garbage collector, one CPU, the application is running with G1 GC or parallel GC. And as we know, one processor, if you have one processor, why you have a parallel GC or a concurrent GC? There's a question. But the other interesting data point is a lot of these applications don't have a GC explicitly configured. So for some reason, the application was running with ergonomics. And potentially the reason G1 GC is being selected here is because there was a bug in the container support. And there have been several bug fixes in OpenJDK about container awareness support. So let's try to understand how ergonomics works for GC selection and why there is some discrepancy here between what the environment is configured for and what the GC selection is providing by the ergonomics. So in Java 11 or later, there are only two garbage collectors that will be considered as per the default ergonomics of the JVM. It's going to be either serial GC or parallel GC. For Java 8, it's serial GC or parallel GC. Again, Java 11, serial GC or G1 GC. Java 8, serial GC or parallel GC. We like to say that for those deploying applications inside containers, the real default garbage collector is the serial garbage collector. And the reason for that is because the JVM will only use G1 GC or parallel GC if the container is running with 2 or more processors and 1,792 megabytes of RAM or more available for the container. Of course, this rule is not specific to containers. This rule is actually specific to the JVM, whether it's running inside a container or not. It doesn't really matter. But as we have seen, a lot of applications are running inside containers and with limited resources. So developers should know serial GC is potentially the default garbage collector in your application. And that may be why you have increasing GC pauses affecting your application function. And what about the heap size? Some developers like to configure the heap size. Some developers don't configure the heap size at all. They just hope the application, the JVM, will be smart and use the container available memory and set the heap size automatically. And it is true, the JVM will have a default heap size. But the default heap size also depends on a variety of things. If the amount of memory is quite small, let's say about 250 megabytes, the JVM will use about 50% of that as the default heap size. If it has more than that, it will use 25%. And depending on other scenarios, it may use 1/64 of the available memory in the system, such as a large server. So in the end, the default heap size actually depends. It depends on the amount of available memory, and it's a moving target in this case. Now, the number of available processors that the JVM sees is also a moving target, and it depends, especially if you're running inside containers. And the number of available processors is an important information by the JVM for a variety of things. It will help frameworks and libraries configure thread pools for doing parallel work. And the JVM itself, the Java platform, has its own thread pool called fork join pool that is used for a variety of things, such as parallel streams. So if you're doing streams in your collections and you're using parallel streams, it will use threads from the fork join pool. So the more available processors that the JVM sees, understands, the more threads will be considered in that thread pool. But if the application is running inside a container, the amount of available processors that JVM sees varies with the information given to the container on the CPU quota, period, and CPU shares. And there's a calculation that will determine how much, what is a processor in this scenario. So if the application has, let's say, 500 millicore, and in that particular container environment, 1,000 millicore is a full CPU cycle, then 500 millicore is half CPU cycle. But for the JVM, that still counts as one processor, either 500, 700, up to 1,000 millicore, that will count as one processor. Anything between 1,001 to 2,000 millicores of CPU time for that container, the JVM will understand it has two available processors. So there have been some issues, of course, with OpenJDK and how it counts CPUs and things like that. So for that reason, you have to watch out which version you're running and if it has these patches or these fixes. So here's just a quick demo that you can look at the screenshot. But on the top left, we have a Java code that will basically print the runtime.getRuntime.available processors. It's an API in the Java, it's a method in the Java API. It will print how many available processors the JVM is seeing, and then running the Java application inside a container and giving only 2 CPUs that processor and 1,500 megabytes of RAM. We use a flag in the JVM called printFlagsFinal, and we will see that it will actually use the serial GC. So even though the JVM can see 2 processors, even though the JVM has 1,500 megabytes of available memory in the system, it's still using the serial GC. And maybe for this application, maybe this is a microservice, IO intensive network calls, 2 processors, and the G1 GC or parallel GC may actually be a better selection for this workload. So as you can see, there's a lot of things at play that if you rely on the ergonomics, you actually don't know what is the garbage collector being used, what is the heap size, how many processors are being used by the application, and things like that. So that's why we like to say, do not have a container in production that simply does Java -jar your application. Because if you do that, you are relying on the default ergonomics. And in a way, the default ergonomics are quite conservative in terms of performance goals, and they are more focused on availability of the application. Make the application run, even though it may run not with the best performance, but make sure the application runs. So that the default ergonomics were designed with that in mind. So to understand more about garbage collectors and when you do that selection, let's look at the options available and let's understand what is garbage collection in the first place. So garbage collectors, they're basically a tool of the runtime to clean up memory. That memory is the heap of the objects that are allocated. The objects that are allocated through the life of your application, they are located in the heap. But we as developers, we don't have to worry about removing these objects from the memory. The garbage collector will do that. So garbage collector is basically, the heap has this object creation and removal event happening all the time. And the garbage collector is this process that runs that will see if this object in memory has any reference to it and move this object here and there until no more references exist. And then the garbage collector feels like, okay, I can remove this object from memory and free memory for more objects. So the thing that happens with applications, if they don't have a properly tuned garbage collector, if the garbage collector is poorly tuned, then the application will see high pause times. You hit an enter on a URL or a microservice endpoint, and it takes quite some time to receive a message because the garbage collector may be working at that time. A lot of the CPU time of the JVM is spent doing garbage collection. And it may even occur out of memory error because the application was not able to release memory before more objects were being created. So it is worth tuning the garbage collector, of course, once you understand what's going on, but it is worth tuning the garbage collector because it can allow you to literally save costs, save spending, especially in cloud environments where cost is related to usage. So if you can tune the garbage collection, if you can tune the JVM properly, you can reduce the spending on infrastructure in the cloud, and that definitely gives you not only better performance, or perhaps equal performance at lower cost. But the ideal scenario is that you can actually hit a better performance at a lower cost by tuning properly your application. But setting the heap size is not enough. We've seen time and again, like, oh, just increase the heap size and the application will work just fine. It is true, giving more heap for a JVM will allow the application to perform better. But just that may not be enough. Does the application has enough CPUs, especially if it's inside a container? Is the throughput meeting the SLAs? Is the latency meeting the SLAs? Sometimes giving more heap, but with the wrong garbage collector, may not give you the best results. Imagine this, you gave a lot of memory, but the garbage collector is still the serial GC because you're still running one processor. Well, what happens is your application will have amazing throughput and great latency speed until the garbage collector needs to run. And when the serial GC needs to run, your application simply pauses. And that is where your application may hit SLA breaches and have performance issues in not meeting customer expectation. So when you're going to configure the heap size, one tip that we do give is that developers should configure using the second flag that we see here, the max RAM percentage. The reason for this is that if you want to increase the amount of memory of your pod or your container, the JVM will automatically increase its heap size because it's a percentage of the available memory. Of course, you can also set hard-coded amounts like 2 gigabytes of RAM, 5 gigabytes of RAM with the classic XMX flag. But if you want some elasticity in the heap inside containers, we recommend using the max RAM percentage. But what about which garbage collectors do what? We put out this table that gives developers some good recommendations. These, they do differ a little bit from the T4 ergonomics. So for example, if you have a Java application that is running on a multi-core container or server, but it's mostly for batch jobs or a microservice with a small heap, let's say it's 1 gigabyte of RAM, 2 gigabytes of RAM. In fact, what we say here is no more than 4 gigabytes of RAM. Parallel GC is a great option. Of course, this is a general recommendation. It doesn't mean that every workload will work best, but you can start with this. If your application has large heaps or needs large heaps, and you have a lot of request response interactions with databases and operations with objects in memory, and more than 4 gigabytes of RAM, you may want to consider G1 GC, which is in a way the most commonly used ones these days. And then there is also the other garbage collectors for extremely low latency, ZGC and Shenandoah GC. These two garbage collectors are for very large heaps. They can be used for mid-size heaps, but the best results for these garbage collectors have been without benchmarks on large heaps. Monica works on our engineering team here at Microsoft, and she has this saying, GC tuning is basically trying to optimize the movement of objects in memory and make them move as little as possible, as late as possible, so as to not disturb the flow of your application. And that summarizes what GCs are meant to be and why tuning them is important, because you want to keep the flow of your application as smooth, as fast as possible. So here's a good summary of where we are with today's presentation so far, after all that have been said. So ergonomics, by default, it's serial GC or G1 GC on Java 11. On Java 8, it's going to be serial GC or parallel GC. The application needs to be running, the JVM needs to be running on an environment that has 2 or more processors and 1,792 megabytes of available memory or more if you're going to rely on the deep ergonomics. Otherwise, you will get serial GC by default. We do suggest parallel GC for microservices, especially those IO-bound microservices. And Heap, yeah, make sure you configure the Heap with the max RAM percentage flag, because then the container doesn't matter. You don't have to change that flag in your container. The ops team can just go and increase the amount of memory of the JVM by increasing the amount of memory of the container. But you have to watch out for off-heap allocations and needs. So let's move on and talk about Java and Kubernetes. Java and Kubernetes, again, there's a lot of things here, but they kind of go back to the containers. So just to recap, CPU throttling is when the application doesn't have more time to be used in the CPU. But there are some misconceptions. Developers tend to believe that 1,000 millicore as the CPU limit of a container means 1 CPU. That is not true. In fact, 1,000 millicore means that the application can consume a full CPU cycle per CPU period. And a full CPU cycle may as well be split across 2 CPUs. So 1,000 millicore, as an example, will still allow an application to run multiple threads in parallel. And as we know, the Java platform is a multi-threaded platform by its nature. It comes with a garbage collector, it has thread pools, it is multi-threaded. Of course, it runs with a single core, but it is multi-threaded. So on Kubernetes, the likelihood of a Java application being CPU throttled is high if you don't properly configure the JVM, the container, and Kubernetes, and your limits. So let's take this example here. You have an application, a Java application, it has 2 threads, and you put a limit of the Java application, 1,000 millicore. But again, it's a multi-threaded application. You have 2 threads coming in, let's say 2 users doing an HTTP request at the same time. One request spends 400 millicores, and the other request spends 500 millicores. And then there's a third thread, let's say the garbage collection thread, consumed 100 millicores. Now your application has to wait 500 millicores. So your application will pause for half a CPU cycle, which is, of course, insignificant for one particular execution, but it can add up quite easily when we are talking about tens of thousands of requests per second, or even more, way more than that. So to summarize, up to 1,000 millicore, the JVM sees 1 processor. From 1,001 to 2,000, 2 processors, and so on and so forth. But there is a way to trick the JVM and say to the JVM, hey, I don't care what you see in the system. I want you to believe that you have a different processor count. And there is a flag to change that. You can actually hard code when you're launching your JVM application. You can say -XX active processor count equals X. And that will override any of the readings that the JVM will do in the system. So to understand a little bit, I have this beautifully designed chart that gives you an idea. So let's say we have this container running in production. It's 1 container, it's 1 Java virtual machine. And you can see at the top, the CPU limit is 1,000 millicore. That is what is configured for this container on Kubernetes. And the CFS period is 100 milliseconds. So that's the idea of the CPU time here. the CPU period. So it is a multi-threaded application. I'm giving a 1,000 millicore limit, but this node on Kubernetes is a 4 CPU VM. The node has 4 processors, which means if I get 4 HTTP requests at the same time, I get 4 threads running in parallel. So these 4 threads will run, be processed, go into the database, get information, etc., and return to the user. Now, these 4 HTTP requests were processed nearly instantaneously, and each HTTP request is spent about 200 millicore of the CPU time. So 4 times 200 millicore gives us 800 millicore. Now, my application, my container, only has 200 millicores left to do work. But all of that happened in 20 milliseconds. The next CPU cycle is still 80 milliseconds in the future. Now, this is a Java application. The JVM is running. There's a garbage collection. The garbage collector runs multiple threads. 2 threads run at the same time. The GC work combined took about 200 millicores. So the GC work took all of the remaining of the CPU time available for this container. And now the remaining CFS period is 60 milliseconds. And my application cannot do anything else because there's no more CPU time left, which means now any new HTTP request that happens here will be throttled. And that is why we see when we do some performance load tests on applications inside containers, inside Kubernetes, we see some spikes of latency happening. And those spikes in latency is what you should be reading as CPU throttling time, because your HTTP request on average, let's say 90%, your P90 is perfect. Like 10 milliseconds HTTP request. In 10 milliseconds, your request gets processed by your system. But your P99 is very bad. So the other 10% gets really bad because it's being throttled. Now, this means that these 2 HTTP requests that got throttled will take at least 60 milliseconds to run instead of 20 milliseconds to run. So in total, they will take 60 milliseconds plus the time they take to execute. So let's assume here 20 milliseconds, 80 milliseconds. So you have a jump from 20 milliseconds to 80 milliseconds because you have 60 milliseconds of CPU throttling time, blocking your application from executing. So when we look at the options and what should we be configuring in general for Java containers on Kubernetes, we believe there are better configurations than the default ergonomics. So we are recommending that developers do these sort of configuration. If the developer believes that the application needs a certain amount of memory that we can see here on the darker blue amount of memory for the system, then that is the amount of CPU and garbage collection that we are suggesting. So for example, up to 1,000 millicore, if that is really what you want to do, we do suggest that you use parallel GC and somewhere between 2 and 4 gigabytes of RAM. And we actually recommend that you do an active processor count equals to 2, just to have a better tuning of your application, especially if this is an IO bound microservice. If your application has 2,000 millicore, we recommend parallel GC or G1 GC, the selection of which will be based on the amount of memory. And one thing to be considered about G1 GC is that G1 GC has, it consumes off heap memory. So even the percentage that you give, you may have to adjust that so that G1 GC can have off heap memory available to do its job. If you're planning to give more than 4,000 millicores to your workloads, we consider G1, GC, and even somewhere ZGC, Shenandoah options are all available. But we do recommend that you consider Shenandoah and ZGC for large heaps, and G1, GC for medium to large heaps. So let's take a look at how these considerations can impact your performance, the performance of your system, and also the cost. So here we have